So I'll be talking about genomic visualizations for biologists in R, and this is based on a package I wrote in R called Manhattanly. A lot of the details you'll be able to find on a vignette that I have on my website there. And I'll just talk about the motivation and just some of the functionalities of the package. I realized when I gave the title for this talk, it might have been a little bit misleading. So just in case, I mean, I won't be talking about this type of genomic visualization or things like that. It's more just basic scatter plots, but there's a reason behind that. And so just to give you some idea of the motivation, I tried to come up with something clever because we're in New York. So that's the Brooklyn Bridge here, and I kind of see the link between statisticians and computer scientists as being relatively close. We kind of speak the same language, especially with the help of R. And I feel like it's almost become a natural kind of bartering system where we kind of trade methods for computer programming skills. But I feel like in my day-to-day, I work a lot with biologists, and they're kind of, on the other side. That's the Manhattan Bridge. And so really, the question is, or the question I'm trying to address with this package is, how can we effectively communicate with people who aren't natural programmers or who don't program all the time? And, this may seem, especially when you're surrounded, with this kind of crowd, or you're doing your PhD and you're working with quantitative people, it might not seem so obvious, but once you start dealing with physicians and neuroscientists and biologists, you kind of see that, okay, this is not something that they can fully grasp, and so you need to figure out a way to translate this. So that's kind of the motivation behind the Manhattanly package. And so I think a lot of tools exist already, and really I'm just standing on the shoulder of giants, and these are some great packages that allow you to translate some of the work that we do, maybe in statistics. And I think a common theme is that they're all web-based. And I think this underlies the fact that maybe not everybody has R or Python, but everybody has a web browser. And so that makes it really easy with these tools to convey these messages. Nobody needs to have these tools installed already. And so I work in the field of genetics and genomics, and over the past 10 years, there's been great development in the types of data that are produced. And so we started way back when with the genome, sequencing the genome, which is basically the ATCG that you see. And then we went on and started getting more complex data, trying to address more the functionality. So what does the DNA actually do, and how the proteins work, gene expression, DNA methylation, things like that. And so that's generated lots of data sets. And so this is what I mean by large. I don't want to get into the big data debate here, but this is what I mean by large. You have lots of features and a small number of samples. And so one of the first analyses you might do on this type of data is something called a genome-wide association study, or a GWAS, which is basically for each of the 450,000 features, you do a t-test or a linear regression. Later on, they came up with something called the EWAS, which is just the same thing, but now for DNA methylation markers. And my personal favorite, something called GWAS, which is a gene environment-wide interaction study. And so this all leads to multiple tests, and it's kind of it might not be the smartest thing to do, but it's the most common thing that's done. Is you conduct a whole bunch of these tests, and then you do some sort of multiple testing correction. And so, as I mentioned before, it's something more about the field that I work in. I deal a lot with many different disciplines, and I think this is something that you need to consider when you're trying to present your method or trying to convey the results of your statistical method that you're developing. You have to be able to talk with biologists and speak almost a different language. And same thing with physicians. And so one way we can convey these results, a popular plotting tool, is the so-called Manhattan plot. And so what we've plotted here is, on the y-axis, a p-value, or some measure of significance. And so in this case, the higher, it's the negative log 10 scale. So the higher means the more significant or more evidence for some function in the disease or the phenotype. And what you see here, basically all these little letters that you see here are the genes where the SNPs are located. And so this is very important information. So it's not only important just to have the name of the SNP, but actually the gene on which the SNP lies, and then what the functionality of that gene is. And so basically what happens in a traditional analysis, as a statistician, you might get this data, you'll run your analysis, and then present the biologist with a list of genes. And biologists love that. They love looking at lists of genes, and because they understand all these words and letters, whereas I have no idea what these mean. So, you know, it's a collaboration. It's very interdisciplinary. But in terms of a plotting tool, it can get quite messy because you only have a few genes plotted here. And on top of that, it's missing quite a bit of information. Another thing you might do is something called a volcano plot. And so what you have here on the x-axis is some measure of effect, so an effect size, a regression coefficient. And on the y-axis, again, it's the negative log 10 p-value. And so this is more for, okay, well, I have something significant, but really how much of a difference does it make? How much of an effect does it have? And so that kind of helps you discern this. And what you can see here is, again, it's very cluttered, especially the text is very cluttered. It's hard for anybody to see. I can't just send this plot off to a biologist for them to expect to understand what these letters are because they're all overlapping. And so it's kind of, again, these are some of the questions that you get asked from the biologist. So what gene is it on? You know, how far is the nearest gene if it's not on a gene? The effect sizes, transcription start sites. There's many different questions, and I feel like with the help of Plotly and these web-based interfaces, you can help answer those questions so that you can send this document to them and they can open it up in their web browser and not have to, they can go and look at it on their own time and then figure something out and get back to you with some sort of interpretation of the results. So this is kind of what led me to answer this question, and I started with this small case study with a very familiar data set, the MT-CARS data set. So I ran a principal component analysis, I did some clustering, and then I plotted these clusters. And so this is just a cluster plot of the data. And so you can see here, and so basically what we're trying to do here is cluster the cars based on some of the features. And so you can see here, okay, that, you know, these cars kind of cluster together, so I put them in one cluster. And here, again, you have lots of text and there's a lot of clutter. And so this is just a ggplot solution. And then if you go a little bit further, someone came up with this ggRepel solution, which is quite nice. So you just, actually it's just a one line of code. You don't have to change anything in your encoding for the plot. And what it does is there's some algorithm going on behind the scenes, and it tries to find the distance away from the point such that it doesn't clutter the plot. And so this is great, it's a nice solution, but it's still, there's only one piece of information there. And so the Plotly solution would be to just remove all text altogether, and then with their hover feature, you can just see exactly what cars you're dealing with. And so this is kind of where I got started with making this Manhattanly package, where I could kind of use the same hover feature to encode lots of information that biologists are interested in. And so this is a plug for my package. That's the website. It's on CRAN. So it's a very simple package. It's basically just a wrapper for a lot of work that Carson did. He's the lead developer for the Plotly package. And so it does three things. It creates these Manhattan plots, these QQ plots, which is just a method of verifying the distributional assumptions of your test statistics, and these volcano plots. And so in the package I've included, this is what a typical data set would look post-analysis. So what you have here is the chromosome number, and this is included in the Manhattanly package, so you can play around with it. But so a typical analysis, you would have the chromosome, the BP, which is the base pair position, a p-value, some measure of significance, and then some other annotation information. And so you can And this is the code to create this Manhattan plot. It's pretty standard. You can put up to 4 annotations. And this is not restricted to SNPs. It could be cortical thickness measures if you're in neuroimaging studies, DNA methylation if you're looking at the epigenome. And then what you get is a plot like this. And so you can highlight, and then you can start seeing. So you see now I've encoded lots of annotation information in each point. And then, you know, if the biologist is looking at this at home on their laptop, you can just zoom in. And I didn't do any of this. This is just all Plotly. It's just a nice wrapper that I've done. But most of the work is being done by the Plotly library. And so you can focus in on a region of interest, and you might want to look at, you know, not only the genome-wide significant SNPs, but the ones that are in LD or linkage disequilibrium, LD, which is just a measure of correlation. So this is nice, something the biologist can appreciate, especially because they understand what these genes mean, and then they can come back to you with some interpretation results. So a similar interface for the volcano plots. You can specify these thresholds, and then you'll get, in this specific example, you would get points that are automatically highlighted if they're beyond the threshold. So that's what you see here in this area. So they're both, these points have a effect size greater than 1, and they meet genome-wide significance. You can also just set one of the thresholds to false, and then you'd get something like this where all the points are, you know, everything above that line is automatically highlighted. And of course, you can also automatically specify the points that you want highlighted. So again, it's a very simple package, but I find it useful in my everyday, especially if you want to convey your results to people who don't use these languages. And then this is the same thing for the QQ plot, which you can see. And so you notice one thing, there's quite a bit of loading time, is because the data set has like 14,000 observations. And so that's kind of maybe you could say a limitation, is that, 14,000 is a lot smaller than what a typical data set would look like. There's other ways to get around it. You might not have to show all these points, especially the ones at the bottom of the plot here. So there's ways around trimming your points, but that's definitely a limitation, is that you're putting a lot of data into these plots, and that could slow down the rendering of the plots. And so just how we're using this and some future directions of how we want to implement this for mainstream use. So we're collaborating with the Montreal Neurological Institute at McGill. And so what they have is this C-Brain portal, which is basically just kind of a front end for people who aren't exposed to programming, who are not programmers. So basically they're researchers, and they have this data, but they don't know how to normalize it, they don't know how to analyze it, but they want to, they still want to conduct these experiments on their own. And so what this platform does is you basically input the data, and there's a whole bunch of things going on behind the scenes. I don't know if you could see all this, but basically, there's a whole bunch of things going on behind the scenes, but what the user sees really is just this kind of web client. And so you can imagine now, using the Plotly or the Manhattanly library, you can just add this to something that the user can see after. So there's statistical analysis that goes on behind the scenes, and then the end user just sees the results and can see all the annotations in a form of a Plotly plot. There's also another collaboration we're trying to start, and this is with Loris, which is a similar idea. And so they have this nice platform where you can do lots of kind of more data integration methods. So the different data types that I was showing before. And so along with these, brain imaging studies, like I said before, the measures of significance are not explicit to SNPs or just genetics, so we can go to neuroinformatics, neuroscience studies. And so again, we can try to include this as a feature so that the end user can see, the different annotations, what cortical thickness is associated with the phenotype. And so there was a speaker earlier today who basically said heat maps are useless. So I think it was Eduardo, if you're still around. I think they're not useless. It's actually the first thing we do when you have large data sets. And so kind of give you an idea of a measure of, correlations are very interesting, especially in neuroimaging studies, to know what area of the brain is correlated with another area, because that kind of gives you some sense of functionality, so they're working together. So Tal Galili came up with this heat apply package, which is the same thing I did with the Manhattanly plots, but he did this for heat maps. And so again, this is interactive, and we're thinking of kind of implementing this on those user portals. So again, just the strengths. I think the main strength for me, at least, someone who doesn't know HTML or JavaScript, is that I'm able to take advantage of all these great tools that you guys are coming up with and trying to get it to the end user, the clinicians, the physicians, the biologists. And I think that's kind of the motivation behind a lot of these tools, starting maybe going back to Markdown. You can share a lot of the results in a very compact format, so it doesn't have to be a list or an Excel file. It can be a lot more visual, a lot more attractive visually, but still convey and still carry all the information that a biologist can use. And then, again, it allows collaborators to look at their own pace. And in my experience, it's a lot easier just to collaborate with people if you just give them the results and they kind of look at it on their own time. And again, one of the limitations, as I mentioned before, was the large number of points can still be an issue, at least for now. But it seems like you guys are coming out with lots of great stuff. So with that, I just want to thank all these great people and the great organizations, Plotly for inviting me to speak, and Carson especially, because he's the lead developer for that Plotly R package, and basically what I'm doing is just wrapping around that. So thanks for your time.
Great talk, thanks. So I'm wondering, my question is, how have you seen biologists use these tools? I'm also in the bioinformatics field, and I built something similar, just basic like volcano plots where you can choose the thresholds. And the biologists have told me, like, this is too complicated, I don't get it. So I'm wondering, have they been using it, and how have you convinced them or shown them how to understand the data?
I've had one person use it so far. But yeah, no, I agree with you. It's really hard to get out of, it's really hard to put yourself in their shoes because you're so surrounded by all these tools, and you think, so many people have done great work in making even HTML accessible to people, I don't know, maybe like me, who don't know that language. And so you think, okay, this is super easy. But yeah, definitely. I think one thing that's helped with that one person at least is the fact that it's web-based, so they like that they can use it on their iPad. A lot of the doctors have iPads, and if we're talking about real, like in the future, we're not talking right now, but real-time results, I think they kind of see the benefit and are willing to put in time for that. But yeah, I feel your pain. It's frustrating when you're putting all this work in and they're still saying, as simple as it is, maybe for us, they still seem it's definitely a barrier.
So, do you support, or do you plan to support adding track lines underneath your Manhattan plots? Because that would be very useful. They always want to know what is the nearest gene or what gene is this in. You could imagine a UCSC-like track line underneath.
Oh, yeah, okay. Yeah, no, I mean, are you saying to integrate it into there?
Not necessarily integrate, but like the ability to add a track line underneath your Manhattan plot would be very, very useful, I think.
Yeah,
is it supported or something you plan on, or?
I haven't thought of that, because yeah, you're right. I mean, for me, the first thing I do is go to the UCSC, so I haven't thought of actually doing it myself. But yeah, no, I think it would take quite a bit of work, but maybe submit an issue and we'll see.
Another potential feature request. Thanks for the great talk. I guess one of the issues that could be hampering the interpretability is that all of the points now are interactive. Could there be an option to add another argument to the plotter that only above a certain log p-value, those points are colored or interactive, and then if you're mousing over the points that aren't even significant, then they're not getting pop-ups all over the place?
Yeah. Yeah, no, I think, yeah, it's a good point. I think the easiest way would just be to do that beforehand. So maybe just filter out some of the points beforehand. I guess I'd have to talk to the Plotly people to see if you can turn off text annotation. I think it's possible. I think I've just done it by default, but you're saying that you could probably save memory and time and space. Yeah, I think, yeah, that's a good point. I think it's possible. Please submit an issue. Yeah.
One of the ways I like to get intuition out of a large statistical genomic data set is gene set enrichment analysis.
Mm-hmm.
Have you considered integrating that, or have you started to?
Yeah. I mean, what you get out of the GSEA is usually a list of pathways, right? So, I mean, you have some idea of what you would want to visualize from that?
I do. Let's talk after.
Okay. Okay. Thanks.